This is week 11 of engineering thermodynamics course problem solving session. So the past week we saw problems regarding second law, mostly concerned with entropy and applying entropy balance to an system. So it can be either an open system or a closed system. It's an extension to what we saw in the first law analysis. So the second law gave you direction and the possibility of a process where it can happen or not, because the second law defines how the process should proceed, and that is given by the entropy. We say that entropy will always increase for an isolated system. So the entropy balance is also similar, where we take into account both the entropy of the system and surrounding and say that the entropy always increases, and you estimate for a system what is the entropy generated. So this will be always greater than b equal to 0. So continuing with the second law analysis, we'll see some more problems today. So let's get started. So the problems will be similar to what we saw in the previous week. So similar kind of problems where we apply the entropy balance and the first law analysis to the system to estimate the properties and the energy balances and so on. So the first question for today is, we have a radiant heating lamp powered by electricity which has a surface temperature of 1000 Kelvin emitting 500 watts. So the radiation is absorbed by surfaces at the ambient, which is at 18 degrees Celsius. Find the total entropy generation and specify where this entropy generation is being made, including how much. So what is there is assume there is a room. So you have a radiant heating lamp. So that lamp, your heater, whatever that, it is powered by electricity. So you are supplying 500 watts and it is getting converted into 500 watts, and it's emitted as radiation. So the surface which radiates heat is at 1000 kelvins. So the lamp itself is at 1000 kelvin, and it is radiating heat which is amounts to 500 watts, and this heat is absorbed by the surfaces which is around it, and it is at ambient temperature of 18 degrees Celsius. So these two things which we know. So one is providing heat and one is absorbing heat. So if you see, this is similar to what we saw in the previous week as well. You have a heat transfer between a surface one where heat is entering and in a surface basically, or a bar. So you have a solid bar where heat is coming in and heat is going out, and both are at different temperature levels. So this is similar to that. So what is asked is, you know, to find out how much is the entropy generation happening and where is this entropy being generated. So first we'll put an control volume across the lamp, because we need to find out where this entropy generation is happening and so on. So we'll put an energy balance across the lamp first. So applying an energy balance in that, so what is coming in is your electricity, which is a form of work. So that is coming in, and because it's a steady state and the temperature is constant throughout, there is no change in internal energy of the system. So internal energy of the system will be 0, and what is going out is your heat which is being radiated. So whatever work which is coming in will go out as heat. So that's what is the phenomenon of an electric heater. So that gives you the first energy equation, which is Q out equals the electric work provided, which is 500 watts. Then we'll apply the second law or an entropy balance for it. So change in entropy or entropy coming in and so on. ds by dt for there is no stream which is coming in, so ds by dt is also a steady state is 0. So this is equal to heat transfer which is happening. So heat transfer to the ambient, so heat is getting rejected. So minus q out by T surface at which the heat is transferring from. So because it's a constant temperature, you can directly write q by T sir, or else it will be an integral dq by T. So q out by T surface plus the entropy generated in the lamp. So the entropy generated in the radiating lamp is q out by T surface, which is 500 by 1000, which gives you 0.5 watts per Kelvin. Similarly, now whatever heat is radiated out by the lamp is now absorbed by the encompassing surfaces. So the space itself is at 18 degrees Celsius, which is taking away the heat in the form of radiation. So this is at 18 degrees Celsius. So whatever, if you apply an energy balance, so q in minus q out is 0. So whatever heat is coming in is getting going out, so it is at 500 watts. So writing an entropy equation, again we will get q in by T in minus q out by T ambient. So the entropy which is generated, which is coming in at the 1000 Kelvin, and one which is going out is at 18 degrees Celsius, because any temperature will always radiate. So here both will radiate, both the ambient and the 1000 Kelvin. So that's what is being done here. So you have q in by T in minus q out by T ambient plus the entropy generated. So what we have now is, so entropy generated in the ambient air is q out by T ambient minus q in by T in. So you have q both same, so it's 500 by 291.15 minus 500 by 1000, which gives you 1.217 watt per Kelvin. So the total entropy generation is the sum of these two, both the radiant element and the ambient. So that comes out to be 1.717. So if you do an energy balance encompassing both the space and the radiating element, so in that case what will happen is electrical in is the energy is coming in, so which is the heat which is radiated out. So the energy which is radiated out from the space is q out by T ambient, so that comes out to be 1.717. So this is similar to what we did the calculation, the sum of both. So entropy is generated both because of the heat transfer in both the element as well as the ambient. So moving on to the next question. An open feed water heater is a direct contact heat exchanger used in vapor power plants. Shown in figure are operating data for an open heater with H2O as the working fluid operating at steady state. Ignoring stray heat transfer from the outside of the heat exchanger to its surrounding and kinetic and potential energy effects, determine the rate of entropy production in kilowatt per Kelvin. So this is an open feed water heater, so where you both streams get mixed and they transfer heat because of that, and you get another stream which will be an intermediate stream of both. So this is the process conditions here. So it's an open feed water heater, one which is coming in at 3 bar and 36 degrees Celsius. There is other stream which is coming at same 3 bar, and but the vapor quality is 0.92. So this is in the form of steam and other is in the form of liquid. So both get mixed, so steam gets cooled in the process and the water gets heated up. So what you are left out with is a 3 bar saturated liquid stream which is going out So this is the process which is happening. So what is being asked is, so indirectly what they mean is ignoring stray heat transfer from the outside of the heat exchanger is that the open feed water heater is adiabatic. There is no heat transfer which is happening. So only heat transfer is because of the fluids getting mixed. So for this process now we need to assume find out what is the rate of entropy production. So the same process can be shown in a TS diagram here. So you have a TS diagram. So this is your vapor dome and this is a constant pressure line because all streams are at constant pressure. Though in an actual case that's not the case, you will have some pressure drops, but ideally what you want is the streams which are getting mixed are to be at the same pressures. So you have the constant pressure bar here, 3 bar, and your stream which is coming in 1 which is at 36 degrees Celsius and 3 bar. So corresponding to 3 bar, if you see in a steam table, the temperature will be higher, the saturated temperature will be higher, which is close to 133.6 degrees Celsius. But here it is at 36 degrees Celsius, so it is a subcooled liquid. So you are here at 1, and then the second stream which is coming in at state 2, which has a vapor quality of 0.92. So this is stream 2. So this gets mixed up and you get somewhere in between, but in this case it is said that it will be a saturated liquid. So you are having a saturated liquid, and what is also given is the mass which is going out is 80 kgs per second. So the total mass is 80 kg per second. So you have m1 plus m2 equals 80 kg per second. So from the stream table it is straight away, so the water property table, you can straight away find out the enthalpies and entropies. So for the subcooled liquid which is at 36 degrees Celsius and 3 bar, the enthalpy will be close to the enthalpy of your saturated liquid at 36 degrees Celsius. There will be not much change. So you can assume it to be a saturated liquid at 36 degrees Celsius, saturated liquid, not 3 bar, but at 36 degrees Celsius. So that will be across something around 150.86 kilojoule per kg, and similarly entropy is 0.5188 kilojoule per kg Kelvin. So why is this isobar line? This will be very close to your saturated liquid vapor boundary as well, saturated liquid boundary. So this will be really very close. So the error will be very small. So we can assume H1 to be equal to the saturated liquid at 36 degrees Celsius. So we have found out enthalpy and entropy at 36 degrees Celsius, and then we need to find out for state 2. So enthalpy at state 2 is again HF2 plus X into HFG. So that gives you enthalpy at state 2 to be 2552.2 kilojoule per kg, and similarly entropy, so entropy comes out to be 6.5663 kilojoule per kg Kelvin. So these are the enthalpy and entropy values. Next is state 3, which is at 3 bar and saturated liquid. So enthalpy is straight away from the table, H3 is 561.47 and entropy is 1.6718 kilojoule per kg Kelvin. So these are the enthalpy and entropy values which we will require to apply the first law and second law analysis to the system. So doing an energy balance and an entropy balance. So that's what we need. So we have found out enthalpy and entropy for each of the states. Then applying in mass balance, as I said, it's straight away m1 plus m2 equals m3. So that's what we get, and we can write m1 the other mass in terms of one of the mass or in any fraction. So then doing an energy balance, applying the steady flow energy equation, what we get is you have dE by dt, which will be 0 equals q minus w plus then in streams which is coming, energy of the streams which is coming in minus energy which is going out. So q minus w plus m1 h1 plus m2 h2 minus m3 h3. So this is what we get, because there is no heat transfer and there is no work transfer which is happening. So substituting M1 as M3 minus M2, we get M2 in terms of M3 and an enthalpy ratio. We get M dot 2 is M dot 3 into H3 minus H1 divided by H2 minus H1. So we know M3, which is 80 kg per second. So substituting the enthalpy values of each of the states, M2 comes out to be 13.68 kilograms per second. So that is the flow rate of mass 2, which is the steam and vapor mixture with a quality of 0.92. Then M dot 1 is the difference between these two streams, which comes out to be 66.32. Now we apply the entropy balance. So we know the enthalpies, we know the mass. So now we can straight away apply the entropy balance for this feed water stream. So again, we have two inlet streams and an outlet stream. So there is no heat transfer between because the open feed water heater is insulated, so there is no heat transfer. And since it's a steady state, you have ds by dt 0. So you get 0 equals integral or summation q by t, which is 0, plus the entropy of the streams which is coming in minus the one which is going out, plus the entropy generated. That is your entropy balance. So q by t is 0. So m1 s1 is your entropy of stream 1 which is coming in. M dot 2 s2 is the entropy of stream which is coming in again, and 3 is your stream 3 which is going out, and the entropy generated because of this two streams getting mixed. So that gives you the entropy generated. So we have found out all three entropies of the three streams, and we know the mass. So m dot 3 is 80, which is given, and m dot 1 and m dot 2 we have already found out. So entropy generated will now be substituting the values, it comes out to be 9.51 kilowatts per Kelvin. So this is the entropy generated. So you can see that entropy generated is positive, and that's what the second law also says, that entropy generated is always greater than 0. So that's what we see here, 9.51. So this inevitably says that this process is irreversible because you are mixing the two streams which is at different temperature. So getting it back is also difficult. You cannot reverse it back, and that is given by this positive value of entropy generated. So that was for a feed water stream. So we'll move on to the next question. We have air at 200 kilopascal and 52 degrees Celsius, and a velocity of 355 meter per second enters an insulated duct of varying cross-sectional area. The air exits at 100 kilopascal and 82 degrees Celsius. At the inlet, the cross-sectional area is 6.57 centimeter square. Assuming the ideal gas model for the air, determine the exit velocity in meters per second, and B, the rate of entropy production within the duct. So what we have is you have a duct, but you have a duct which has a cross section which is varying. I don't know if you the best example is to see a centralized air conditioned building where you will see such kind of ducts which are generally insulated as well, because you don't want to lose the cold air. So this is an example of that. You have an insulated duct, and there you will see there are some sections which are the area gets reduced. So here also is an example. We have a cross sectional area which is getting reduced, and the inlet cross sectional area is given, and the velocity and conditions, pressure and temperatures are given for both. So we need to find out what is the exit velocity and the rate of entropy production. So we'll see how to solve this. So what we have is three kinds of balance. We have mass balance, we have energy balance, and an entropy balance. So let's start with the first, the mass balance, the simplest. So in this case, we have a duct. So whatever mass is coming in will always go out. In a steady state, there is no accumulation of mass inside this duct. So mass coming in is always the mass going out. So and then energy balance. So you have applying the steady flow energy equation, you get dE by dt, which is 0, equals Q minus W plus the energy of stream which is coming in minus the energy of the fluid or stream which is going out. So here, since it's insulated, you have there is no heat transfer and there is no work transfer as well. So Q minus W is both are 0, and then what you have is we can assume the potential energy to be 0. So since there is a area change and there is a velocity change, so you need to consider the kinetic energy. So you have m dot h1 minus h2 plus v1 square by 2 minus v2 square by 2 equals 0. So a little bit of rearrangement, it will give you v2 as root of v1 square plus 2 times h1 minus h2. So we can get v2 out of this. So we know the inlet velocity. We also know the air's pressure and temperature for both inlet and outlet. So we can find out the enthalpies using an air standard table. So we can straight away find out the enthalpies. So we know we can find out enthalpy, we know velocity at in. So substituting that, we get V2 to be 254.5 meters per second. So that is your velocity which was asked. So we got straight away got the velocity. So this is similar to a nozzle which we did. So the second is to find out the rate of entropy generation, and that will apply an entropy balance again for this duct. So say again, say the steady state process, you have ds by dt which will be 0, and then again there is no heat transfer since the duct itself is insulated. So we assume there is no heat transfer, so Q is also 0. So what we get is m S1 minus S2 is equals to the entropy generated, and we can find out entropy generated as the change in entropy of the stream, outlet minus inlet. So m dot is again applying in for ideal gas model. So this is what we get. So S naught T is your temperature entropy with respect independent of pressure. So S naught T minus S naught 1, this will get directly from the table. So assuming you at your adiabatic ambient pressure, so and just the entropy with respect to the temperatures. So that's why you get S naught T minus S naught T1, and minus R ln P2 by P1 gives you, takes into account the change in entropy because of the change in pressure. So we get S naught T2 minus S naught T1 minus R ln P2 by P1. So we know both pressures and temperature. So we can substitute, we can find out the entropies and we can substitute the pressure values here. And we know R for gas, this is air. So 8.314 divided by the molar mass of air. And since area is given, it is 6.57 centimeter square, we know velocity and we know the inlet conditions of air. So we can find out the density of air. So using density, you get you can find out mass flow rate, which is rho times A into V. So that gives you 0.5 kilograms per second, and then substituting the values, you get the entropy generated to be 0.144 kilowatt per Kelvin. So next question, we have students in a laboratory are studying air flowing at steady state through a horizontal insulated duct. So one student group reports the measured pressure, temperature and velocity at one location in the duct as 0.95 bar, 67 degrees Celsius and 75 meters per second respectively. So the same group reports the following values at another location in the duct, which is 0.8 bar, 22 degrees Celsius and 310 meters per second. The group neglected to note the direction of flow on the data sheet. However, using the data provided, determine the direction of flow. So is it from the point 1 to 2 or from 2 to 1? So that's what we need to find out. So to do that, we'll find out what is the entropy generation from point 1 to 2, and if it turns out to be negative, it says that the process can happen only from 2 to 1. So that's the general idea of determining how the process is happening. So if the entropy generated for flow happening from point 1 to 2, so we initially will assume that 0.95 bar, 67 degrees Celsius and 75 meters per second, it lies at the inlet, and the flow is happening from this point to the other point 2, which is at 0.8 bar and 22 degrees Celsius and 310 meters per second. So we assume this is the flow direction from point 1 to 2, and we'll estimate what is the entropy generated. And if the entropy generated turns out to be positive, this says that this process is possible, and the flow is the assumption of the flow direction which we made is correct. If it turns out to be negative, then it also says that the direction which we assumed is wrong, and the actual direction is the opposite of our assumed direction. So to start with, we'll assume one direction, and that is from 1 to 2. So to determine the direction of flow, let us apply the entropy rate balance at steady state. So assuming the direction of flow as shown above, so this is what I said. So at steady state, applying an entropy balance equation, so ds by dt is 0, and again there is no heat transfer since this is an insulated duct, so there is no heat transfer. So q by t is 0. So what we get is ms1 minus s2 plus sigma, which is the entropy generated. So sigma is the entropy generated per mass rate of flow. It gives you s2 minus s1, it should be greater than 0. So finding out what is the entropy generated, and so s2 minus s1 from ideal gas equation. So the same what we did in the previous case. So s0 t2 minus s0 t1 minus r ln p2 by p1. So substituting the values again here, what we get is s2 minus s1 to be 0.0934 kilojoule per kg Kelvin. So this turns out to be negative. So the assumption which we made of the flow happening from state 1 to 2 is false, or the actual flow is the other way around. It's from the 0.8 bar state to 0.95 bar state. So let's move on to the next question. We have ammonia which enters the compressor of an industrial refrigeration plant at 2 bar and minus 10 degrees Celsius with a mass flow rate of 15 kg per minute and is compressed to 12 bar and 140 degrees Celsius. So we have a ammonia compressor the inlet to the compressor is at 2 bar and minus 10 degrees Celsius, and the mass flow rate is also given at 15 kg per minute. And they say the compression happens to a pressure of 12 bar and 140 degrees Celsius. So during this compression process, there is a heat transfer which is occurring from the compressor to its surrounding at a rate of 6 kilowatt. So the heat transfer is also given. So for steady state operation with negligible kinetic and potential energy effects, determine the power input to the compressor, which is in kilowatt, and the rate of entropy production in kilowatt per Kelvin for a control volume enclosing the compressor and its immediate surrounding, such that the heat transfer occurs at 300 Kelvin. So with the pressure and temperature, we find that for the ammonia, both inlet and outlet are at superheated state, which is generally the case which we want. We don't want any liquid to be present for the compression. So we can straight away find out what is the enthalpy and entropy values from the superheated table for ammonia. So it turns out to be H1 is 1440.31 kilojoule per kg, and H1 which is the entropy at inlet is 5.6781 kilojoule per kg Kelvin, and the enthalpy at exit is 1757.26 kilojoule per kg, and entropy is 5.7850 kilojoule per kg Kelvin. So now to determine the power input to the compressor, so we assume that compressor to be a control volume, and we'll apply the first law to the compressor. So the steady flow energy equation to the compressor, we get 0 equals Q minus W plus the energy coverage of the stream which is coming in with the inlet minus the exit. So assuming the kinetic and potential energy of the stream is to be 0 or negligible, the change is to be negligible, so you get kinetic and potential energy can be neglected. So you get Q minus W plus m dot H1 minus H2. So the rate of heat transfer or the heat ejected by the compressor is given. What we need to find out is the work which is applied to the compressor, which is the WCV. And since we know the inlet and outlet conditions, we know the enthalpies. So the only unknown will be the power which is supplied to the compressor. So WCV is QCV plus m dot H1 minus H2, and QCV is minus 6 kilowatt since heat is rejected from the compressor to the ambient. So it's minus 6 plus we know the mass flow rate, which is 15 kg per minute. So 15 divided by 60, which is 1 by 4, multiplied by the change in enthalpy, which is 1440.31 minus 1757.26. So the total work which is supplied, or the power supplied to the compressor, is minus 85.24 kilowatt. So this is negative because the work is supplied to the compressor, so that's why it's negative. So next is to find out what is the entropy balance or the entropy generated. So the compression process, this is at steady state, so we have ds by dt is 0, which turns out to be QCV by T plus the entropy change of the stream, in minus out, plus entropy generated. The heat transfer is 6 kilowatt, and the surrounding temperature is at 300 Kelvin. So minus 6 by 300 plus 1 by 4 into the entropy change, which is 5.7850 minus 5.6782. So this comes out to be entropy generated is 0.9 0.4673 kilowatt per Kelvin. So next question. A refrigerant R22 in a refrigeration system enters one side of a counterflow heat exchanger at 12 bar and 28 degrees Celsius. The refrigerant exits at 22 bar and 20 degrees Celsius. A separate stream of R22 enters the other side of heat exchanger, a saturated vapor at 2 bar and exits a saturated vapor at 2 bar. The mass flow rates of the two streams are equal. I think this is 12 bar. I think there's a mistake here. So the refrigerant exits at 12 bar and 20 degrees. Cannot exit at 22 bar. Okay. And 20 degrees Celsius. So what's happening is one side is getting cooled and other side is getting heated. So the mass flow rates of the two streams are equal. The stray heat transfer from the heat exchanger to its surrounding and kinetic and potential energy effects are negligible. So what it means is the whole heat exchanger is insulated and only heat transfer happens between the two streams. There is no other types of heat transfer. So heat lost by one stream is heat gained by the other stream, and rest there is no other heat and work transfer, or there is no heat transfer crossing the boundary of the heat exchanger. So with this assumption, we also take what is determine the entropy production in the heat exchanger in kilojoule per Kelvin, kg Kelvin of refrigerant flowing, and what gives rise to the entropy production in this application. So we know that mass flow rates are all same. So we can assume m dot 1 and m dot 3 is m dot. So substituting in a steady flow energy equation for the heat exchanger, there is no heat and work transfer which is crossing the boundary of the heat exchanger. So only form of energy which is coming in and going out is the energy transferred by with fluids, or the enthalpy carried by the fluids. So what we get is m dot h1 minus h2 plus h3 minus h4, m dot h3 minus h4. So what we have is here is h4 is h1 minus h2 plus h3. So because we don't know what is the temperature at the superheated vapor. You know the pressure, because in here we assume there is no pressure drop, so that's what is happening. So we are having inlet at saturated vapor and we want it to be superheated. So the amount of superheat which is happening we don't know, so we need to find out the temperature at state 4 to know the condition. So inlet is known, outlet of the stream 1 is known, the stream 2, the inlet is known but we don't know the outlet. So H4 is H1 minus H2 plus H3. So H1 is 12 bar and 28 degrees Celsius, and 12 bar and 20 degrees Celsius. So that assuming both are in subcooled conditions, 28 and 20 will be in subcooled condition corresponding to 12 bar for refrigerant R22. So we can straight away look up at saturated liquid enthalpies corresponding to saturated temperature of 28 degrees Celsius and saturated temperature of 20 degrees Celsius. That gives you the enthalpy and entropy. So the first one, H1, then comes out to be 79.05 kilojoule per kg, and entropy comes out to be 0.29636 kilojoule per kg Kelvin. And similarly from the table, H2 is 69.09 kilojoule per kg and S2 is 0.2607 kilojoule per kg Kelvin. And H3, which is saturated vapor at 2 bar, is 239.88 kilojoule per kg, and S3 is 0.9691 kilojoule per kg Kelvin. So H4 comes out to be H1 minus H2 plus H3. So H4 is 249.84 kilojoule per kg, and then interpolating using the enthalpy and pressure value. Pressure is of 2 bar and enthalpy is 249.84. We find that temperature is T4 is minus 9.815 degrees Celsius. So that is the temperature, and this is in the superheated state because we are using a refrigerant. So the saturated temperature corresponding to 2 bar for R22 is 2 bar is minus 25.18. So my inlet stream 2 is a 2 bar and minus 25.18 as saturated vapor, and it is exiting at a temperature of minus 9.815, which is a superheated state, which is much higher than minus 25. And the entropy corresponding to this pressure and enthalpy values is 1.0081 kilojoule per kg Kelvin. So doing an entropy balance gives us so since the steady state equation, so ds by dt is 0, and there is no heat transfer which is happening across the system to the surrounding. So q is 0, summation q by t is 0 plus, so what we get is the entropy change between the streams, so which is m dot S1 minus S2 plus m dot S3 minus S4 plus the entropy generator. So entropy generator rearranging, and you get entropy generated per unit mass. We get the entropy differences of the inlet and stream 1 and stream 2. So S2 minus S1, so we get 0.2607 minus 0.2936. So this, there is a reduction in entropy because one is getting cooled and other is getting heated. So here entropy is 1.0081 minus 0.9691. So that gives you entropy generation of 0.0061 kilojoule per kg Kelvin. So this is the entropy which is generated, and this entropy is generated because the heat is transfer is happening between two different temperature levels, and that is what causing this entropy generation. And that in actual case there will be a pressure drop across the heat exchanger because of frictional pressure drops, because there will always be friction to the flow, and that will cause additional entropy generation. But in this case we assume that pressure drops to be 0. So next question, we have a room air at 23 degrees Celsius is heated by a 2000 watt space heater with a surface filament, temperature of 700 Kelvin. The room at steady state loses the power to the outside, which is at 7 degrees Celsius. Find the rate of entropy generation and specify where it is made. So this is similar to the first problem which we saw today. So what is the entropy generation? So we can straight away use that. So the heater entropy generated is again the heat transfer, because entropy generated because of heat transfer. So minus dq by t. So 2000 watts of heat is getting generated. So 2000 by t is 2000 by 700. So it gives you 2.857 and then applying to the space between the heat and the room, so which is at 23 degrees Celsius, room is at 23 degrees Celsius. So which is heat is coming in at 700 and 700 degrees Celsius and going out at 23 degrees Celsius. So the entropy generated because of this heat transfer, so minus 2000 divided by 700 minus of minus 2000 by 296. So that gives you 3.9 watts per Kelvin. So that is the entropy generated because of the heat transfer in the ambient or the room. And then this heat is now rejected to a ambient which is at 7 degrees Celsius. So that will be entropy generated is again the heat transfer change. So minus 2000 divided by 296 minus 2000 divided by 280. So that gives you entropy generation of 0.389. So if you see here, one more observation which you can make is because the temperature difference at the second case where the space between heater and room is very large, and that causes a very large rise in entropy generation. And similarly, when you come across the wall which is at 23 degrees Celsius and 7 degrees Celsius, this the temperature difference is not that large compared to what was there between heater and room. So here if you see, what you have is 1/10 of the entropy generation. So the largest entropy generation is because of the largest temperature difference which is happening, because it is inversely proportional to T. So next question, an insulated cylinder piston has an initial volume of 0.15 meter cube and contains steam at 400 kilopascal and 200 degrees Celsius. The steam is expanded adiabatically and the work output is measured very carefully to be 30 kilojoules. It is claimed that the final state of the water is in two phase, which is a mixture of liquid and vapor. What is your evaluation of the claim, whether this is true? So what is said is, you have an insulated cylinder piston. The initial volume is 0.15 meter cube and it is containing steam which is 400 kilopascal and 200 degrees Celsius. So that is the initial condition. We know pressure, temperature and volume at the start, and the steam is expanded adiabatically. So because insulated there is no Q heat transfer, and the steam is expanding adiabatically, and the measured work is 30 kilojoules. We need to find out whether the state 2 is a two phase state. So this is a closed system. So applying first law to the closed system initially, so you get a change in internal energy to be Q minus W, and we know Q is 0 in this case. So whatever work done is goes into change in the internal energy of the system. So m u2 minus u1. So to find out, first we need to find out how much mass is there. Since we know the volume and we know the pressure and temperature, we can estimate the specific volume. So initial volume divided by specific volume, so that gives you 0.15 divided by 0.5342, which comes out to be 0.2808 kilograms. So mass we know, so 0.2808 kilograms, and the initial state internal energy is 2646.8 and entropy is 7.1706 kilojoule per kg Kelvin. So since this is an adiabatic case and we assume it to be reversible process, so both S2 and S1 is equal. So that comes out to be S2 is equal to 7.1706 kilojoule per kg Kelvin. So applying substituting the internal energy and work done in the energy equation, so U2 equals U1 minus W by M, so which we get 2646.8 minus 30 by 0.28808. This comes out to be U2 is 2540.0 kilojoule per kg. So using this U and the entropy value, so checking and interpolating in the table, so we find that Ug is 2540 corresponding to the saturated gas. Your entropy is 7.0259. So this entropy which we have is greater than the saturated gas entropy. So it states that state 2 is in superheated state and not in a two-phase state. If S1 would have been lower than 7.0259, then we can say that it will enter a two-phase state at the exit, or else it will always be a fully vapor, and in this case it is a superheated vapor. Next question, we have a piston cylinder which has a water volume separated in a VA of 0.2 meter cube and VB of 0.3 meter cube by a stiff membrane. The initial state in A is 1000 kilopascal and quality of 0.75, and in B it is 1600 kilopascal and 250 degrees Celsius. Now the membrane ruptures and the water comes to a uniform state at 200 degrees Celsius with heat transfer from a 250 degrees Celsius source. Find the work, the heat transfer and the total entropy generation in the process. So what is given is, first initially you have two separate chambers with water being occupied. So the initial states of these two separate volumes of water is given, the volume is given and the condition which they are in are given. So what is happening is the membrane is getting, which is separating these two set of volumes, is getting ruptured. So now the two waters will get mixed. After mixing it, there is also a heat transfer which is happening from 250 degrees Celsius source. So because of which they say that the final water mixture is at 200 degrees Celsius. So we know the final state. So we need to find out how much, what is the work done and what is the heat transfer which is happening. So here this is not a rigid vessel but having a piston cylinder arrangement. So we have two, there is a piston, I think better to draw. So something like this, you have anyway. So we have a piston, suppose this is a cylinder, and then you have two separation. So initially this is the piston, and then this is the membrane which is separating both the volumes. So it's your piston cylinder arrangement. Okay. So this is how the arrangement looks. So you have A and B. So in this case, in first we'll apply, since it's a closed system, there is no mass transfer. So the mass at state 2 is the sum of the individual masses in both the volumes. So M1A and M1B. And similarly, the energy balance is the change in internal energy, which is M2U2 minus the individual volume internal energies equals Q minus W. And when you apply heat transfer, there is heat transfer. So when you take the initial and final state and consider all of the process together, applying an entropy equation is the change in entropy of the system, which is M2S2 minus the initial entropies equals the heat transfer Q by T plus the entropy generated. So in this case, what is happening is the process, the pressure is constant throughout, since at any point there is only the piston weight and the atmospheric pressure which is acting on the piston from the top, which is balanced by the pressure of the fluid. So there is a pressure is always constant. So initially state 1A, assuming the volume in 1A, the state 1 for this is initially the quantity is 0.75 and pressure is given as 1000 kilopascal. So we can find out what is the specific volume. So we need specific volume to find out the mass, and then internal energy and entropy. So specific volume comes out to be 0.146117, and the internal energy comes out to be 2128.15 kilojoule per kg, and similarly entropy is 5.47445 kilojoule per kg Kelvin. And state 1B is for 1600 kilopascal and 250 degrees Celsius. So specific volume is 0.14184 meter cube per kg, and internal energy is 2692.26 kilojoule per kg, and entropy is 6.6732 kilojoule per kg Kelvin. So using this, now we can find out the mass, individual masses. So M1 is V1 by specific volume 1. So it just comes out to be 1.3688 kg, and similarly mass at the volume B is the volume B divided by specific volume of B, which comes out to be 2.115. Now at state 2 we know that pressure is at 1000 kilopascal, and it's at 200 degrees Celsius, so it's at superheated vapor. So V2 is 0.20596 meter cube per kg, and U2 is 2621.9 kilojoule per kg, and S2 is 6.6939 kilojoule per kg. So here in this case we assume this to be a massless piston. So since piston weight is not given, so we assume this piston to be of negligible mass or having massless. So the pressure which is applied by outside, it should be equal to the pressure inside. So outside side is your atmospheric pressure, which we assume. So M2 is M1A plus M1B, which comes out to be 3.4838 kilograms. So V2 is M2 V2 is 3.4838 into 0.20596, which comes out to be 0.7175 meter cube. So integral PdV, since it's a constant pressure process, so P equivalent to change in volume. And change volume can be found out using the final volume. So we know the total mass. So total mass divided by multiplied by the specific volume at state 2 gives you the final volume, which is 0.7175 minus the initial volume, which is 0.5. So the work done is 217.5 kilojoule. So that is the amount of work which is obtained because of this process. And Q2 is again the change in internal energy plus the work done, which is from the first law. So that comes out to be 744 kilojoules. And the entropy generated is the entropy change of the water minus the entropy change because of the heat transfer. So minus Q by T. So the resource temperature is at 250 degrees Celsius. So substituting the values, we get the entropy generated to be 0.2908 kilojoule per Kelvin. So next question, we have water in a piston cylinder is at 1 megapascal and 500 degrees Celsius. There are two stops, a lower one at which V minimum is 1 meter cube and an upper one at V max of 3 meter cube. The piston is loaded with a mass and outside atmosphere such that it floats when the pressure is 500 kilopascal. The setup is now cooled to 100 degrees Celsius by rejecting heat to the surrounding at 20 degrees Celsius. Find the total entropy generated in the process. So what is happening is your piston cylinder arrangement with two stops, one with a volume of 3 meter cube and another with a volume of 1 meter cube. So initially the piston is loaded with a mass and outside atmosphere such that it floats when the pressure is 500 kilopascal. So when your pressure inside is 500 kilopascal, the piston will start moving. That's what they say. So the mass and the outside pressure balances pressure of 500 kilopascal. So that is given, and the setup is now cooled to 100 degrees Celsius by rejecting heat to the surrounding at 20 degrees Celsius. So what is happening is initially the piston is at the maximum volume 1 meter cube, 3 meter cube, and it has some higher pressure. So this which is at 1 megapascal and 500 degrees Celsius. So at 500 kilopascal it will start moving. Now it is at 1 megapascal. So it will be at the topmost position of 3 meter cube and it is at 500 degrees Celsius. So it will cool initially. So it will be at constant volume process till it reaches a pressure corresponding to 3 meter cube, and then it will start falling the piston and it will have a constant pressure process of constant pressure of 500 kilopascal. So once it reaches 500 kilopascal, the piston, then it's a constant pressure process. There is only volume change which is happening because at any point your pressures are getting balanced. So you'll have a constant pressure, and then once it reaches this the second stop, which is the lower stop, which has a volume of 1 meter cube, then there's again a constant volume process. That's what is shown in the PV diagram. So initially you are at 1 megapascal, this 1000 kilopascal, and temperature of 500 degrees Celsius. Initially of cooling it is a constant volume, then a constant pressure, and then a constant volume process. And a similar is shown in a TS diagram. So here you have a constant pressure process which is equivalent to a constant temperature for pure fluid. So the first case, the initial volume initial specific volume is 0.35411, and the internal energy corresponding to 1 megapascal and 500 degrees Celsius is UNS 3124.3 kilojoule per kg Kelvin, and S is kilojoule per kg, and S1 is 7.7621 kilojoule per kg Kelvin. So the mass is initially it will be at 3 meter cube with the topmost stop. So that is 3 meter cube. So V by V1 gives you 3 by 0.35411, which comes out to be 8.472 kilograms. So that is the amount of mass of water in the piston cylinder arrangement initial, or steam in. Next, we need a final state which is at 100 degrees Celsius. So corresponding to following intermediate states, so 1 dash and 2 dash, for example. So we get Vg is 500 kilopascal, which is 0.3749. So this will be greater than the specific volume initially, because it follows a constant specific volume. So we take V1 is Vg of 154 degrees Celsius, and Tsat at 500 kilopascal is 152 degrees Celsius, which is again greater than T2. So V2 is heat bottom plus divided by mass, so which is 0.118 meter cube per kg. So we know the specific volume at state 2, which is equal to the 2 dash here. So we can find out the quality. So x2 is 0.118 minus 0.001044 divided by the difference in specific volumes. So which gives you 0.0699. So this is corresponding to 100 degrees Celsius. So you get U2 is 418.91 plus x into U of G, which is 564.98 kilojoule per kg, and similarly S2 is 1.73 kilojoule per kg Kelvin. So applying first law. So here the work done for the system is integral P dV. So since it's the only work done which happens because of the intermediate process where the volume is changing, so we'll have P delta V. So what we get is minus 1000 kilojoule. So we get work done to be minus 118 kilojoule per kg. So 1000 divided by the total mass, that is 8.472, it gives you minus 118 kilojoule per kg. So that is the specific work, and the total heat transfer which is happening. So applying first law, we get change in energy plus the work done. So what we get is minus 22683.4 kilojoule, or specific heat is minus 2677.5 kilojoule per kg. So whatever heat is getting rejected, it is happening at 20 degrees Celsius to the surrounding. So what we have is applying the entropy balance. We have S2 minus S1 equals Q by T plus S generated, the entropy generated. So you get entropy generated to be M S2 minus S1 minus Q by T. So that gives you 26.27 kilojoule per Kelvin. So next question, we have two tanks contains steam and they are both connected to a piston cylinder as shown in figure. Initially the piston is at the bottom and the mass of the piston is such that a pressure of 1.4 megapascal below it will be able to lift it. Steam in A is at 4 kilograms at 7 megapascal, and 700 degrees Celsius, and B has 2 kilograms at 3 megapascal and 350 degrees Celsius. The two valves are opened and the water comes to a uniform state. Find the final temperature and the total entropy generation, assuming no heat transfer. So, this is the arrangement. You have two tanks which is connected with the valves to a piston cylinder arrangement, and what they are given is the piston floats when you have a pressure of 1.4 megapascal. And initially the steam at A is having container A as 4 kilograms of steam at 7 megapascal and 700 degrees Celsius, and similarly at B is 2 kilograms at 3 megapascal and 350 degrees Celsius. Now they are opening the two valves and the water comes to a uniform state. So both gets mixed and they form a uniform state. Find the final temperature and the total entropy generation, assuming no heat transfer. So once all the valves are opened, what will be the final state, and assuming no heat transfer. So first, the combined mass on both tanks is Ma plus Mb, which is mass at state 2. It comes out to be 6 kilograms. So 4 plus 2, which is 6 kilograms. And similarly energy balance, so we have M2 U2 minus the energy balance in each of the tanks equals Q minus W. So since heat transfer is 0, which comes out to be minus W. And similarly entropy balance, there is no heat transfer, so Q by T is 0. So this is the entropy difference between the steam system equals the entropy generated. So based on the initial conditions for tank A, so specific volume at tank A is 0.06283 and the internal energy is 3448.5 and entropy is 7.3476 kilojoule per kg Kelvin. So and the volume is 0.2513 meter cube. This is your mass 4 divided by 0.06283. So 4 into 0.06283 gives you 0.2513 meter cube. And similarly for tank B, the specific volume is 0.09053 and internal energy is 2843.7 and entropy is 6.7428. So the final volume is 0.1811 meter cube. So the final volume only when the piston rises or reaches steady state is when the V2 is greater than Va plus Vb. That's the case when P2 can lift, and in that case you have constant pressure process. So your work done is P2 into change in volume, which is V2 minus Va minus Vb. So substituting this in the energy equation above, we get M2 U2 minus M AUA minus MBUB equals minus P2 V2 minus Va minus Vb. So rearranging, what we get is M2H2 equals MAUA plus MBUB plus P2 Va plus Vb. So substituting the values here, we get 4 into, substituting the values, we get M2H2 as 20,086.8 kilojoule. So H2 is M2H2 by M2, so M2 is 6 kilograms, so we get H2 as 3347.8 kilojoule per kg and a pressure of 1400 kilopascal, which is the pressure at which the piston gets lifted. So corresponding to this, we get a volume V2 specific volume as 0.2323 meter cube per kg and entropy as 7.433 and temperature of 441.9, which was asked. And finding out the final volume V2 is 1.394 meter cube, which is greater than the sum of the other volumes, which states that the assumption is correct and the piston is getting lifted up. And that also can be used to find out how much work is being produced. And then finally the entropy generated is just the entropy difference between the initial and final states. So final and initial states. So we have 6 into 7.433 minus 4 into 7.3476 minus 2 into 6.7428 gives you entropy generated as 1.722 kilojoule per Kelvin. I think this is the final question which I have for today. With this, I'll end the session. So the final question is: a cylinder fitted with a piston contains 0.5 kilograms of R134A at 60 degrees Celsius with a quality of 50%. The R134A now expands in an internally reversible polytropic process to ambient temperature of 20 degrees Celsius, at which point the quality is 100%. Any heat transfer is with a constant temperature source, which is at 60 degrees Celsius. Find the polytropic exponent n and show that this process satisfies the second law of thermodynamics. So what is given is we have a cylinder with a piston and it is initially containing 0.5 kilograms of R134A at 60 degrees Celsius, and the quality is also given as 50%. This R134A is expanding and it is an internally reversible polytropic process. We need to find out the polytropic exponent, and ambient temperature is 20 degrees Celsius, and the final is it's at 100% quality. So that means the saturated vapor. So heat transfer which is happening is that happening at a constant temperature of 60 degrees Celsius. So we'll see how to solve this. So the process which the R134A undergoes is PV raised to power n equals constant, which is the polytropic process. And we know that mass will be same, it's a closed system, and applying first law, the change in energy is Q minus W. In entropy equation, S2 minus S1 equals integral dQ by T plus the entropy generated. So T1 is at 60 degrees Celsius and X1 of 0.5, so that gives you a pressure of 1681.8 kilopascal, and the specific volume is 0.006207 meter cube per kg, and entropy is 1.4948 kilojoule per kg Kelvin, and U1 is 347.1 kilojoule per kg. And similarly state 2, which is at 20 degrees Celsius and quality of 1. So here P2 is again 572.8 kilopascal and specific volume is 0.03606 meter cube per kg, and entropy again is saturated vapor, it is 1.7183 kilojoule per kg Kelvin, and U2 is the saturated vapor internal energy, which is 389.19 kilojoule per kg. So this is all from the table based on the information given. So the process is PV raised to power constant, so we can write it as P1 by P2 equals V2 by V1 raised to power n, because mass is constant. So n is nothing but ln P1 by P2 divided by ln V2 by V1. So substituting the P1 and P2 pressures, we get n to be 0.6122. So that is the polytropic index. Next we need to find out what is the whether the process is possible, whether it satisfies the first law. So for that, first we will estimate what is the work done, because we need to find out what is the heat transfer which is happening. So to do that, we will first find out the work done, because we know the internal energies, we only unknown is the heat. So we can find out work done for a polytropic process. So expansion is the integral P dV. So we get P2 V2 minus P1 V1 divided by 1 minus n. So substituting, we get work done to be 13.2 kilojoules. So entropy generated is ms2 minus s1 minus qh by th. So the heat transfer which is happening is from the first law, substituting mu2 minus u1 plus w comes out to be 34.2 kilojoules. So substituting that here, and here heat transfer is happening with this temperature source of the 60 degrees Celsius. So entropy generated is 0.5 into is a 0.5 kg of gas multiplied by the entropy change minus 34.2 divided by 333.15. So it comes out to be 0.0092 kilojoule per Kelvin. So since the entropy generated is greater than 0, this satisfies the second law, and this process is possible. With that, I finished problems with the second law. So next we have one more week which will deal with some cycles and processes, and then we'll have one more review session, and which is would be on next Tuesday and Thursday, and we'll close the session for today. Thank you.